Hello everyone, my name is Kaihe from Simultaneous University. This summer, I worked under the mentorship of Professor Basti and PhD student Shibo at Air Lab in Carnegie Mellon University Robotics Institute Summer Scholars Program for the project titled Real-Time Neural SLAM with LiDAR Data. So in this project, our motivation is how to combine SLAM and NeRF to do dense reconstruction in outdoor things with LiDAR data. Since there are many past works only use RGBD data in indoor thing, and currently the traditional method odometry cannot output the mesh as the dense reconstruction. In our setting, using LiDAR data has less constraints and the scene is much bigger than only a room level scene, which costs more in both time and memory. So overall, our contributions are mainly in threefold. We produce the first LiDAR SLAM with implicit neural representation, and two stages optimization achieves real-time and high-accuracy dense reconstruction for large-scale environments. Lastly, we propose a novel method for neural localization with LiDAR data and achieves state-of-the-art results. Then I will introduce some related works. Zhu and others propose a method that adapts multi-level feature grids for scene representation to enhance scalability and reduce computational overhead. However, it falls short of delivering satisfactory whole filling capabilities due to its localized updates. One and others combine coordinate and sparse parametric encoding for scene representation, striking a balance between real-time performance and memory efficiency. However, this representation cannot expand to outdoor things since the size of the scene is predefined and cannot be incremental. And also, it will cost a lot of memory and cause serious hash conflicts. Zhong and others propose a method for large-scale mapping that learn and store implicit features through an octree-based hierarchical structure, which is sparse and extensible. These implicit features can be turned into sign-distant values through a shallow neural network. However, it relies on the known and accurate poses for mapping, which cannot learn the poses and do mapping at the same time. Inspired by the past works, we present a novel neural LiDAR SLAM system. We implement a two-stages method for each frame. The first stage is only do LiDAR tracking. We sample from the input LiDAR frame and query the SDL value from the neural SDL field, then calculate the SDL loss and then optimize current LiDAR pose. And the second stage is we do boundary adjustment, like the traditional SLAM method. We sample from the current point cloud and a keyframe buffer. And here we optimize pose and the neural SDL field together, so we optimize the pose and geometry at the same time. And for our scene representation, which is exactly our neural and SDL field, we input a coordinate XYZ and quality feature in the octree, and concate the position encoding together as an input to a small MLP to get the SDL value. Here, the reason we use octree is because in the big scene reconstruction tasks, we need to do the data structure should be incremental and efficient, and also easy to implement. Then for our keyframe selection, we found our incremental mapping method suffers catastrophic forgetting in large scenes, like when the LiDAR sensor moving forward, the new data may influence the past features on the octree grid. Just like here, the left grid and right grid share two middle features points. So once you finish the optimization of point cloud from left LiDAR sensor and do optimization of point cloud from the right LiDAR sensor, it may lose the left information. So we keep the last 30 frames as a keyframe buffer, and each time we sample from it when we do boundary adjustment. And for sampling the points to create the training pairs, we employ the TSDF value here. We sample two kinds of points, near surface points and free space points. Near surface points are points within the truncation distance from the LiDAR point along the ray. Free space points are simple points beyond the truncation distance from the LiDAR point along the ray. Then we calculate the TSDF value and generate the training pairs. Finally, here's our tracking results and the quantitative comparison with other methods. We found our estimate odometry is really close to the ground truth, and our RMSE results shows our method achieves the minimal error compared to other methods. Here is our mapping results. You can see our dense reconstruction has very fine detail. And here is our another mapping results, which shows that our method can incrementally build the map. So for our future work, firstly, we want to implement it on real robots. We intend to deploy and evaluate our system on real-world robotic platforms, validating its performance and effectiveness in practical scenarios. Secondly, we want to use both LiDAR data and RGB image data for dense reconstruction. Exploiting the RGB information, we aim to enhance the dense reconstruction process, leveraging the complementary visual cues to enrich the quality and accuracy of the reconstruction scenes. And finally, I want to thank Rachel, John, Shibo, Basti, and all friends I met in this program, and all people working for this race program. Thanks for listening.